Geometric sequences now. So these are sequences in which the ratio between pairs of terms are constant. What do I mean? Well, if I take 4 divided by 2, I get 2. If I take 8 divided by 4, I get 2. If I take 16 divided by 8, I get 2. So to generate any term in this sequence, I need the first term, and then I need to multiply by this common ratio a given number of times. So if I wanted to generate the fourth term, I've got the first term multiplied by 2 3 times. So that would be 2 times 2 to the power of 3. In the second example down here, let's find the common ratio. So to find the common ratio, I want to divide one term by its predecessor. So let's look here at 1/6 divided by 1/2, and that's going to be 1/6 times by 2/1, which is 1/3. Now you might see this much quicker as saying, well, I can quite plainly see that if I just multiply these by 1/3, then that's going to give me my common ratio, and that's absolutely fine. The reason that I show you this is for an example that we'll come up across a bit later on. So again, if I want to generate this third term in my sequence, what do I need to do? I need the first term multiplied by that common ratio this time. How many times? Well, one less than the term number that I'm looking for, which is going to be 2. So the third term in this geometric sequence is given to us like this. Again, we look at some notation. So this is going to be my nth term. What else do we have? We have A is still our first term, and R is now our common ratio. So to generate any term in this series, this sequence, beg your pardon, it's going to be the first term multiplied by the common ratio to the power of n minus 1. So let's go ahead and use that. So we are given that the third term in a geometric sequence is 15, so I'm going to write that down as u3 is equal to 15. And I know that the seventh term, so u7, is equal to 135. I also know that the general way of writing down a geometric sequence is ar to the n minus 1, so that gives me two other ways of noting these things down. That first one is going to be ar squared is equal to 15, and this one here is going to be ar to the 6 is equal to 135. Now again, I've got simultaneous equations. This time they're multiplicative simultaneous equations, and the way I'm going to solve these is by using division. So if I write this out underneath, I'm going to divide these equations by each other. That will cancel the a's and leave me with r to the power of 4, and this will leave me with 9. Taking the fourth root of this, I'm going to get here the square root of 3, or specifically plus or minus the square root of 3. Now, I know that all terms in this are positive, so actually I can ignore the negative here and just deal with r being positive root 3. I still haven't worked out what the first term is. For that, I need to go back into that first equation, so I'm going to then use a times root 3 squared is equal to 15, and that's going to tell me that a times by 3 is equal to 15, or that a is equal to 5. So now I have a way of generating the nth term in the sequence, and it's to say that that's going to be 5 times by root 3 to the power of n minus 1. So if I need to generate that 10th term, it's going to be 5 times by root 3 to the power of 9. What does that give me? It gives me 405 root 3 as an exact value. Now, as I mentioned earlier, there was a reason why I was showing you the division method for finding this common ratio, and it's for this question. The first three terms of a geometric sequence are 4x and x plus 8. Given that all terms in the sequence are positive, we want to find a value for x. So I know that the common ratio is going to be x divided by 4, and I know that this is going to be the same all the way through. So x divided by 4 should give me the same number as x plus 8 divided by x. That's what defines it to be a geometric sequence. Now it's in this format, I can easily cross multiply, so this is going to be x squared is equal to 4x plus 8. Recognise that this is quadratic, so set it equal to 0, and then realise that I can, apparently mismultiply, because what I should have here would be 32, and what I should be subtracting here is also 32, which is equal to 0, and then I can factorise this down into x minus 8 and x plus 4. So the value of x is either going to be 8 or it's going to be minus 4. Now again, I'm told in this question that we are dealing with positive numbers here, so I know that x is 8 and it cannot be minus 4. In the last question, we're going to look at a sequence 5, 20, 80, in which is the first term to exceed 5 million. So just a different phraseology, but again similar to other questions that we've looked at where now we've just got a different unknown to look for. And I can't get rid of that mark, never mind. The first term in this series is going to be 5, and the common ratio in this series, again sequence, get my terminology right, is going to be 4. What am I looking for? I'm looking for when un exceeds 5 million. So when that's greater than 5 million. Well, when does that happen? Well, the nth term is going to be a times r to the power of n minus 1. R we know is 4, so we want to know when that exceeds 5 million. So then I just solve this like an equation. So 4 to the power of n minus 1 is greater than 1 million. Now as we look at this and we realise that the unknown is an indice, it should encourage us to start to use logarithms. So what I need to do now is I need to take logs in base 4 of 4 to the power of n minus 1, which will be greater than logs in base 4 of 1 million. And this, using my logarithm laws, is going to become n minus 1, lots of logs in base 4 of 4, but again we should know that logs in base 4 of 4 is going to be 1, because anything where you take the logarithm of its base is just 1. We end up with n minus 1 is greater than, I pop into my calculator logs in base 4 of a million, and I come back with 9.965 something or other. So n must be greater than 10.965 something or other. Now again, n is a natural number here. It has to have an integer value. So it needs to be greater than this, because it would take the value of 5 million if n were to be exactly 10.96 whatever. So the first one to exceed 5 million is going to be when n is equal to 11.